So now we move on to question 2 of the 2022 scholarship physics paper. This one's called Waka Houra. The history of sailing in New Zealand goes right back to the original settlement of ancestors of Maori more than 700 years ago. The ancestors from Polynesia designed double-hulled boats with triangular sails called Waka Houra that were strong, stable, and most importantly, able to sail into the wind. This allowed them to carry out exploratory voyages, and from such exploration, they were able to plan and carry out their migration to Aotearoa. Waka Houra are able to sail against the wind by heading at an angle to the wind, as shown in the simplified diagram below right. As measured by a stationary observer, the initial wind velocity is 10 meters per second from the north, so let's label that. So this is 10 meters per second. And the velocity of the Waka Houra is 6 meters per second northeast, so this is 6 meters per second. And the final wind velocity is 10 meters per second towards the southwest, so this is 10 meters per second again, in the opposite direction to the velocity of the Waka Houra. Okay, part 1 of question A. By considering the wind direction before and after striking the sails, use impulse and momentum to explain how the wind produces a force on the sails. So again, we're using impulse. We're using impulse and momentum to think about forces. So, what happens here? The wind has changed from going south at 10 meters per second to southwest at 10 meters per second. Now, the wind, or technically the air has no change in the magnitude of momentum, has no change in magnitude of momentum, because it was 10 meters per second before, 10 meters per second after. But there was a change in the direction of the momentum. So before it was going south, now it's going southwest. So air does experience change in direction of P. If the momentum changes direction, and because this momentum is a vector quantity, then the momentum has changed. There is a change in the momentum of the wind or the air, and so the wind or the air is experiencing an impulse. And so we know that F equals delta P over delta T. And because delta P is non-zero, delta P does happen. The P does change between before hitting the sails and after hitting the sails. That means a force is exerted on the air for it to change directions, right? The force is exerted on the air by the sails. Now we know Newton's third law. Newton's third law says that there's an equal opposite forces, right? The sail, as it's exerting force on the wind, at the same time the wind is exerting an equal opposite force back on the sail. And so what we have here is that force exerted back on sail. And that's it. So now we move on to part 2 of question 2A. Explain how the wind produces a force on the Waka Houra that has a component in the direction that the Waka Houra is traveling. Use the grid below to draw a vector diagram to help your explanation. The vectors for the initial wind velocity VWI and the final wind velocity VWF and the velocity V of the Waka Houra are drawn on the grid to help you. Start your answer by finding the vector for the change delta VW in the velocity of the wind. Okay, so this requires a good understanding of how vectors work. And so we're trying to justify how this change in momentum of the wind, how this change in the momentum of the wind produces a force that acts in the same direction that the boat is traveling in. So they've asked us to start by identifying this delta VW, this vector. So what is delta VW? Delta VW, we know, is VWF minus VWI. Because it's the final minus initial. What does this look like on a vector diagram? Well, we have VWF here, and we have VWI here. And what we're concerned with is not VWI, but it's actually negative VWI. So actually what we need to do is invert this vector. So let's see, we kind of have to draw this to scale. So let's see how many boxes VWI takes up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So VWI takes up 10 units. So VWI negative must also take up 10 units, but in the opposite direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So somewhere around there. So negative VWI would look something like this. This would be negative VWI. And so delta VWI must therefore be, because as we know, when we add vectors, we go from tail to head. So the head of this and the tail of this, because we start at yeah, so we go from the tail to the head, and so the vector delta VW is equal to this. So this is delta VW. Now, because of Newton's third law, the change in velocity of the wind here, also the change in momentum of the wind, same thing, has to cause an equal and opposite force on the sails. And so the sails themselves must experience a change in velocity or a change in momentum in the exact opposite direction. So we get something which looks like this, and that's delta V, let's call it B for boat. And now this is to do with the velocity of the boat now. But we know that the velocity must be pointing in this direction, not in whatever direction we have found. What we can do here is resolve this into components. So we could do this and then do this. This is the vector component of delta VB, which is perpendicular to the velocity of the boat. Oh. And this small vector here is the momentum or the vector component of the delta VB, which is parallel to the velocity of the boat. So basically what we've done here is we've resolved the momentum delta VB to two components, one parallel to V and one perpendicular to the V. Why do we do that? Because the one perpendicular to V, this one right here, has no effect on the forward movement of the boat. Sure, the boat might be pushed off to the side, but in a forward direction, which is what we're concerned with, it has no effect. But on the other hand, this forward or this parallel component, does have an effect on V. In fact, it is what is causing the V in the first place. It is allowing that acceleration in the forward direction to allow the boat to move forward. And so, based on these vectors, we can identify exactly how the wind produces a force on the Wakahura that has a component, which we have just identified, in the same direction of V. So in this direction. So now we move on to part B of question 2. The motion of the Wakahura combined with the motion of the wind changes both the apparent speed and direction of the wind hitting the sails. On board the moving Wakahura, the wind appears to have a high speed and to come from a direction further towards the front of the Wakahura. The captain measures the wind velocity as 14.9 meters per second that hits the sails at an angle of 28.4 degrees, as shown in the diagram on the right. And the sails have a combined area of 40 meters squared, and the density of air is 1.23 kilograms per meters cubed. Calculate the mass of air that hits the sails each second. Now, they've asked us to calculate the mass of air which hits the sails each second. And this is not a typical physical quantity that you'll see quite frequently, like something like velocity or time. But it is still something that we can figure out just by showing an understanding of the physics involved. So what do they tell us? They tell us the density of air is 1.23, and that is a very key number because the mass of air, if you haven't come across this concept before, but density, which is given by this symbol which looks like a P, but it's called rho. It's a Greek letter called rho. Density is equal to mass divided by volume. Now, we want to figure out the mass of air, which is the sails each second. So we're concerned with M is equal to rho V. And so we have the density of air. And now all we have to figure out is the volume of air, which hits the sails. And we know that volume of air is given by, let's say for like a cube. If we knew the area of this face, let's call that A. And we knew this length here, let's call that, D. Then the volume of the cube is equal to AD. It's equal to that cross-sectional area times the distance that the cube goes across in that direction of D. So how do we apply that in this situation? Well, we know the cross-sectional area. We sort of know the cross-sectional area. It's not exactly perpendicular to the wind, but we will account for that later. For now, let's just consider that the area is 40 meters per second. 40 meters squared. So we know... let's say, I'll just redraw it. So combined here, we have an area of 40 meters squared. But the wind hits the sails at an angle of 28.4 degrees. And so what basically happens is, if you have wind which is coming head on, then all we have to figure out is that, this length of wind, let's call that D, times this 40 meters squared is equal to the volume of air. And because we're dealing with velocity here, and velocity is measured in meters per second, then the velocity of wind is also equal to, let's see, d over t. It's equal to the distance that the wind will travel in 1 second. And so, since they tell us to calculate the mass of air that hits the sails each second, all we have to think about is the velocity and how that plays into the amount or the distance of air which it covers in that 1 second. But the thing is, the air doesn't hit the sails head on. It hits the sails at an angle of 28.4 degrees. So what we're actually concerned with here is how much of that velocity vector actually is in the component, actually has a component which is hitting the sails head on. So if this is the original velocity vector, then it must have a component looking like that, which hits the sails at a perpendicular angle. Okay, so what is that velocity then? So we know that we can do some trigonometry. Sine 28.4 degrees is equal to, let's see, this V, let's call that V H for head on, and this is V because it's the original V. So it's equal to VH over V. And so therefore VH equals V sine 28.4 degrees, which is equal to, we know that V was 14.9 meters per second. So 14.9 times sine 28.4 degrees. And that is equal to 14.9 times sine 28.4 degrees. Let me just check my calculator's set in the right mode. Oh, it's set in radians. Okay, degrees. Okay, so that gives me an answer of 7.09 meters per second. So that means every second, 7.09 meters of air is hitting the sails head on. So that means every second we have this block of air with a depth of 7.09 meters because it travels that distance in 1 second, and an area of whatever the sails is, so 40 meters squared. So that means the volume of this entire block of air is equal to 40 times 7.09, which is equal to, that times 40, 283.5 meters cubed. And then we move back to this density formula. So M equals rho V equals 1.23 times 283.5 gives us a value of 348.7 or 349 kilograms. And that happens every single second. So now we move on to part C of question 2. The sideways force of the wind on the sails causes the Waka Hura to tilt over sideways. In strong winds, the upwind side of the Hiwi hull may lift out of the water altogether. Part 1 asks, explain how the double hull design of the Waka Hura helps it stay upright in strong winds. You may wish to add information to the diagram to illustrate your answer. Okay, so this question is a consideration of mechanical principles to explain why the Waka Hura can stay upright because of its design. So basically it's asking us, why does the Waka Hura not tip over to the right here and just completely capsize? Why does the double hull design help with that? So what happens? Well, we have a center of mass, I don't know, somewhere on here, and acting through that center of mass is a weight force. Now what happens is, because it's a double hull design and there's like this tipping point on the right hand side here, we have this distance between the weight force and the tipping point or the pivot point. And what happens if you have a force acting perpendicularly at a distance, perpendicular distance from some sort of pivot point? Well, you have a torque. So torque is Fd, and it's the force times perpendicular distance. And here we have exactly that. The force here is the weight force, and there is a distance, in fact, between, or a perpendicular distance, in fact, between the weight force and that hull on the right. So how does that help us? Well, this torque, if you imagine it sort of acting downwards and then causing the boat to sort of rotate in a direction, you can sort of imagine that the torque is, forcing the boat to rotate, what's this? Counterclockwise. So torque from W, or the weight force, acts counterclockwise. And what's also apparent is that this force hitting the sails from the wind, you can sort of imagine it that it's tipping the boat to the right, and so it's tipping the boat clockwise. So torque from wind acts clockwise. Notice how the torque from the weight force is in the opposite direction to the torque from the wind. And so basically what's happened is that because we have this double hull design, and because we have this perpendicular distance right here between the weight force and that right side hull, we have a torque which acts in the opposite direction to the torque from the wind. And so this design has helped mitigate the effective torque from the wind, and helped mitigate the boat from rotating too far clockwise or too far to the right, and that helps it stay upright even in strong winds. So now we move on to part 2 of part C of question 2. Explain how the tilting of the waka hora will affect the force produced by the wind hitting the sails. Again, this is using inferences from your understanding of mechanics. So before, the sails were like this, perfectly vertical, and the wind would hit it face on, right? But now the sail is like this, tilted off to the side, and the wind is no longer hitting it face on. The wind is hitting it at an angle. And so basically what's happened is, if you imagine the extreme case where the sail is completely horizontal, then the wind is passing over it and not hitting it at all. And so you'd expect that between here and here, there is a decrease in the force produced by the wind hitting the sails. So before it was at a maximum because the wind is hitting the sails face on, and then afterwards it is at a minimum, it's at 0 because the wind does not hit the sails at all. It just passes straight over it. So at some intermediate point, which is what we have here, or what we have in the tilting of the waka hora, we would have a decrease in the force produced by wind. So now we move on to part D of question 2. Due to the sideways component of the force from the wind, the velocity of the waka hora is in a slightly different direction to the direction that the hull is pointing. The slight difference in directions creates an asymmetrical flow of water around the sides of the hull, which produces a sideways force on the hull of the waka hora, as shown in the diagram on the right. Explain the effect that the sideways force produced by the water flow around the hull will have on the direction of motion and on the ability of the waka hora to stay upright in strong winds. So this is another explain question using mechanical inferences. And now this question has 2 components to it. So firstly, how does the sideways force produced by the water affect the direction of motion of the waka hora? And secondly, how does it affect its ability to stay upright? So what's happened here? Because let's imagine the waka hora is looks like this, and the velocity of the waka hora is like slightly offset. So that's the velocity. That means any water which is flowing sort of like this way, it will be acted against, the boat will be pushing against the water on the right hand side because it's moving to the right hand side. If you imagine that the boat has a component of velocity in this direction, so v, let's say right, then that velocity in the right hand side direction will oppose the force flow of water and so push against the water. And likewise on the left hand side, because the boat is moving away from the water is able to flow along the boat better. So basically what's happened here, and they've sort of told this to us already, is that the water acts against the sideways component of the velocity by acting in this direction, which is what they've told us here. So how does that affect the direction of motion? Well, if the water's force is acting in towards the left, and the velocity of the Wakahura, or the right hand, sorry, the velocity of the Wakahura is moving off to the right a bit, well then the force produced by the water will counterbalance that velocity moving to the right a bit. And so instead of it being skewed off all the way to the right like that, the force produced by the water will actually skew it back towards the middle a bit more. It doesn't skew it back completely because it's not strong enough to counteract the wind completely, but it will skew it back towards the direction in which the Wakahura is pointing a bit more. And so the direction of motion is, you'd say that the let's see, the sideways component velocity of velocity will decrease, and so it's straighter. So the Wakahura has a straighter trajectory. Okay, that's the first part of the question. The second part of the question is asking how it affects the ability of the Wakahura to stay upright in strong winds. Well, we sort of had this before, and how the Wakahura would be lifted out of the water like this. So let's redraw that diagram. Hopefully I can redraw it quite well. Looks somewhat like that. So if we imagine that the wind is hitting like this, so this is let's call that wind, and the Wakahura is sort of like flowing forward, but off to the side, off to the right a bit. So it's like forward and off to the right a bit. So this is the velocity of the Wakahura. And we know that because the Wakahura is moving slightly to the right, there is a force against the Wakahura from the water, which is slightly to the left, as we can see here. So the force from the water, or from the flowing water, acts to the left. And so before, we had this torque from the wind, which was pushing the boat, and you can sort of imagine it would want to push the boat to the right and push the boat clockwise until it capsizes. Now, if you imagine instead the effect that the water flow has on the Wakahura, this water wants to push the boat to the left, but the water is acting at the point sort of underneath, or at the hull where it's underneath like the surface of the water. So the water is pushing against the hull towards the left, and you can sort of imagine that it will want to kick this hull to the left, up, and then sort of cause the whole boat to turn clockwise as well. And so what's happened is the torque produced by the water flow is in the same direction as the torque produced by the wind. And so the two torques sort of supplement each other to the point where it helps, or not, it doesn't help, but it increases the amount of tilt that the boat would experience. So you'd say that the Wakahura is less able to stay upright. You'd expect there to be greater tilt, and you'd also expect that if the wind or if the force produced by the water flow were strong enough, then this torque would be so great that the boat is turned clockwise to the most extreme, such that it just completely capsizes.